All right, we're going to look at a review problem before we get into any of the new items. We're loop number 29. This was not assigned, but we're going to just run through the example. So if you have your book with you, or if you have a friend, a neighbor that has a book, please look together. We're going to go through number 29. It's page 403. It's the apple question. We're going to look at run just through those two examples, or that one example, talk about how we can verify normal distributions, or how we can talk about unusual observations or not. Right, so it says an orchard owner knows that he's going to have to use about 6% of his apples that he harvests for cider because they will have bruises or blemishes. He expects the tree produced about 300 apples. Part A says to describe an appropriate model for the number of cider apples that may come from the tree. Justify your model. So really what this is asking is, given our information, given what we're looking at, we need to know, should I be using a binomial situation? Should it be a geometric? Is it normally distributed? In the future, we're going to have several more models to look at. What you want to walk away from this question with is that you are going to have to choose between what rules to apply and what formulas apply. On the AP exam, you're not going to have anybody telling you, here's your binomial section and here's the normal section. It's simply going to be a question, and everything is fair game. So you have to be able to look at that, and some things can kind of double. For example, the normal model can approximate the binomial if the sample size is large enough. Okay, in this case, you actually can, because my sample size is 300. We can check a couple of conditions and maybe use that. But let's look at this one kind of straightforward. We know that, well, number one, does it have success or failure? And it's either a cider apple or it's not going to be. So success or failure is definitely checked, right? It's satisfied. It tells us that the probability of being an apple for cider is 0.6. It's about 6%, and that remains constant. And the third thing we look for is independence. This one, because we're using a finite population, meaning that they're not infinite, we're going to have to check 10%. Otherwise, we would think that if an apple is a cider apple or not, one apple's result isn't going to affect another apple's result. So the potential to be independent is there. We just need to make sure that we have a large enough sample size in order, or small enough actually, so that we don't have more than 10% of the population. When we look at that, would be we're taking apples from a certain orchard, and we would assume that the apples off the tree, the one tree produces 300 apples, and so we would assume that his entire orchard would produce more than 3,000 apples. That is definitely, I don't even know how many apples are produced in one full orchard. I know I've been to several orchards, and there's lots more than just a few trees. So our model is going to be represented by the binomial model, and that's represented, the symbol is binomial using BINOM, parentheses N, P. So that's showing a sample size and probability of success. You can see there in the red box what the notation looks like. Normal is used, we just put a big N and put mean a standard deviation in place. Make sure that you know how to write that out. If it was geometric, you would have simply written GEOM and gone from there. Okay. Part B. It asks us about at most 12 apples. And so the question says, find the probability that there will be no more than a dozen cider apples. So that would be at most 12, no more than 12. We've already determined that it's binomial, and so we just simply write it out like this. Binomial is effective. The PDF would be like doing P of 0 plus P of 1 plus P of 2 plus all the way up to 12, and then adding them all up. So that, because we're going over one value, we have to use a CDF. So binomial CDF of 300 0.6 or 0.06 and 12. If we add all that together, it gives us 0.085, or just almost 8.5%, or exactly 8.5%. Okay, part 3, or part B, excuse me, or C, it says, is it likely that there's more than 50 cider apples? Well, in order for us to do this, we have to verify that the distribution can be modeled by normal models, so that I can use area under the curve and stuff like that. So that way we can just look at the standard deviations away from the mean we are, and that would give us an idea if this is a usual or unusual observation. So let's go ahead and check our success or failures. We have n times p. This is going to be 300 times 0.06. That gives us 18. This is not just the number of successes, but this is our expected value. This would be the average number per tree we would expect to have to be cider apples. Okay, n times q also turns out to be quite a bit more. And so that would say, because these are greater than or equal to 10, the sample is large enough to use the normal model. Something in addition to knowing what the mean is, which is 18, we need to know the standard deviation in order to find the z-score. So the standard deviation formula is here. It's n times p times q, and then we square root that value, and you're going to get 4.11. Next, let's look at the normal model. So we'll go ahead and map this out. The question is, could I have 50 or more if my average is 18? And 50 is quite a bit of ways away, especially if my standard deviation is only 4 or just over 4. So you can pretty much tell from this point that it's going to be very unlikely to occur. But let's just go through the motions and find out my evidence. And by the way, if you were to simply say, yes, it's unusual, and provide no evidence, then you haven't given me any justification for that answer. So here's my z-score formula. So we plug that stuff in, and we find out that it's 7.8 standard deviations above the mean, which is incredibly far above the mean in terms of standard deviations. So we would say it's very unlikely that a single tree would bear more than 50 apples that would be used for cider, because my standard deviation is outside 2 standard deviations away from the mean. And that's effectively all for number 29. This problem should have been relatively easy for anyone to complete at this point in our chapter. So we've seen this problem a number of times, so I hope this was a good review for you. This wasn't anything special or surprising. Alright, we want to talk about a couple more things. Something that we haven't exactly talked about yet, and I've mentioned this in passing, but is the shape of the binomial and geometric distributions. What I'm going to do is I'm going to look at some distributions. I'm going to give you the information that I graphed it with, and we'll look at it. So for binomial distribution, basically I took a binomial, a very small distribution, and binomial, we're discussing shape at this point, so be careful not to describe this as normal. It is symmetric and single peaked, but remember the normal model, we're not really kind of describing that. We're just going to be talking about, is it symmetric, is it skewed left or right, stuff like that. So binomial with a 0.5, you can model this if you want to look, and in your list you could go in and set up in L1 you could go 0 through 4, and in L2 you could use your binomial PDF and fill in all those values, and you could look at that and make a histogram by hand. It's a little tricky to make that on the scatter plot or the calculator, because you have to kind of do it a little tricky way, but you could do this by hand, or you could just justify looking at the numbers and see if it's symmetric or if it's skewed left or right. If you look at the next one, this is for 0.2, so it's very unlikely to occur, so that's why you have a low probability to start with, and then eventually it kind of picks up, but and then for 0.8 you get the other way around. So you can see what happens when you change the probabilities to the shape of your binomial and geometric or binomial distributions. Now, geometric is not the same, because geometric doesn't have a limited number of trials. So geometric has one shape. I just picked 0.5 as the geometric PDF as the probability of success, and this is what you get. As you go along the probability of success, you're simply multiplying together, so the probability goes down, 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 and the further out you go, the more unlikely it is. Now, it doesn't always it's not always perfectly skewed to the right, but it will be skewed to the right in some shape or form. Make sure that you know the shapes. You can play around with this using your binomial PDF or geometric PDF, and using L1 and L2. You can just look at the numbers and make your own histograms just scratch on your paper. I want to go through and give you some problems to practice. This is in the chapter, the unit review. Probability unit was chapters 14 through 17. And I've picked a couple out that dealt specifically with binomial and geometric probabilities, and I want you to work through those. This is kind of a review. I will be posting a topical list for the test. They'll be up probably tomorrow. I'll be back on Tuesday so we can talk about that. We'll have a practice run, do some more things like that. But here's some good problems. I want you to spend the rest of the period looking through these. If you haven't finished the ones I assigned earlier, make sure you do that. I will be taking some of these up for a daily grade on Tuesday, so make sure that you complete a selection of these. Make sure that you do some don't just do 7, 9, and 10, but go through each one and look at the different examples that have and try some of those. Work together, help each other out, and we will talk about it tomorrow. If you have a question, you could probably email me at whenever you watch this, and I probably would respond, assuming I'm not busy. So I will see you tomorrow.